Theorem: let n and n dash be the normed linear space and a transformation T n to n dash is a linear transformation, then T is continuous if and only if it is bounded. Now proof: we shall show that T is bounded. Suppose, if possible, T is not bounded, that is, there exists no k greater than 0 such that norms T of x is less than k, norms of x for all values of x belongs to n, then for any natural number small n, however large, there is some vector xn such that norms of t xn is greater than n into norms of xn, or norms of t xn upon n into norms of xn is greater than 1, or norms of t xn upon n into norms of xn is greater than 1. Equation 1: let yn equals to xn upon n into norms xn, then norms of yn equals to norms xn upon n into norms xn equals to 1 upon n tends to 0 as n tend to infinity, which shows that the yn tends to 0 as n tend to infinity. But from 1 it follows that norms of t yn is greater than 1. This implies that t of yn does not tends to 0 as n tend to infinity. Thus the sequence yn converges to 0, but the sequence tyn does not converges to t0. Hence t is not continuous at the origin, which is contradiction. Hence T must be bounded. Conversely, suppose that T is bounded. To prove that T is continuous, now it is sufficient to show that T is continuous at the origin. Suppose that xn tends to 0, then it will be sufficient to show that txn tends to t0 equals to 0. Since T is bounded, there exists a non-negative real number k such that norms of t of x is less than norms of k into norms of x for all values of x belongs to n, then xn tends to 0, which implies norms xn tends to norms 0 equals to 0. Therefore norms txn is less than k into norms of xn tends to 0, and hence txn tends to 0. Hence T is continuous at the origin and therefore continuous.